Welcome back, everyone. So, if you've ever looked at a black plastic pipe, a protective cable coating, or even just a heavy-duty trash bag and wondered exactly what gives it that deep color and UV resistance, well, the answer is usually carbon black. But how do manufacturers know exactly how much carbon black is locked inside that plastic? Today, we're going to explore the answer. In this explainer, we're demystifying the rigorous and honestly fascinating scientific process of extracting and measuring carbon black from plastics. It is a literal trial by fire. All right, let's jump right into ASTM International Designation D1603-01. Now, I know these standardized documents can look kind of dense at first glance, but they're actually the hidden, rigorous rulebooks that govern the manufacturing of almost every everyday material around us. This specific standard gives us a highly reproducible scientific roadmap for stripping away the plastic to reveal the pure carbon black hiding underneath. So, what's the secret sauce here? Well, understanding how this test works fundamentally comes down to one massive, very important word: gravimetric. Basically, we're determining the quantity of a substance by measuring its weight before and after a specific physical process. And in our case, that process is pyrolysis. We are literally weighing the materials before and after they're essentially destroyed by intense heat. We weigh the whole sample, we burn away the plastic, and we weigh what's left. Sounds simple, right? Well, as you'll see, the execution requires absolutely incredible precision. Here's our roadmap for today's explainer. First, the scope of ASTM D1603. Then we'll look at the combustion apparatus, purifying the nitrogen, the pyrolysis procedure, and finally, calculating carbon black content. Let's get to it.
Section 1. The scope of ASTM D1603. Establishing our boundaries.
Right off the bat, there's a super strict boundary we have to draw. This test is specifically built for olefin plastics, namely polyethylene, polypropylene, and polybutylene. It does absolutely not apply to plastics with acrylic modifications, polar monomers, or brominated flame retardants. Why? Well, remember, this is a weight-based test. If you throw in non-volatile pigments or complex flame retardants, they just won't burn off cleanly. They'll leave their own ash and residue behind, which would totally wreck the accuracy of our final weight. The standard demands a clean burn, so we've got to start with the right materials. Moving on to Section 2, the combustion apparatus, the testing environment.
Okay, if we trace the flow here from left to right, we've got our nitrogen source entering the system. The gas travels through a purification and flow measuring stage right into the center where the real magic happens, the electric furnace heating up our little porcelain boat. Finally, the gases exit on the right, bubbling through a series of glass traps. And notice those traps at the very end? They're actually filled with trichloroethylene. And that first one, it's completely submerged in a beaker of solid carbon dioxide, dry ice, just to catch any volatile byproducts before they can escape into the fume hood.
Now, to build this setup, the standard demands some seriously high-end hardware. You absolutely cannot just use a standard lab oven. We're talking an electric furnace that's at least 20 centimeters long, a high-temperature glass combustion tube, usually Pyrex or Vicor, that's twice the length of the furnace. The sample itself sits in a glazed porcelain, quartz, or even a pure platinum combustion boat. Plus, we've got to monitor the heat with a specialized iron Constantan thermocouple capable of reading up to 700 degrees Celsius and control our gas with a hyper-precise flow meter. Every single piece is a specialized tool designed to handle extreme temperatures without degrading and throwing off our critical weights. Section 3. Purifying the nitrogen, a truly critical safeguard. Here's the deal. If there is even a hint of oxygen in our tube, the carbon black will literally catch fire and burn away to ash. We'd have nothing left to weigh. We want pyrolysis, not combustion, which means thermal decomposition without oxygen. So step 1, we start with pre-purified nitrogen containing less than 0.01% oxygen. Step 2, we scrub it even more. The standard lets us bubble the gas through a potassium hydroxide pyrogalis solution or run it over a plug of hot copper tinsel that acts kind of like an oxygen sponge. Step 3, our ultimate goal, we have to get the oxygen content hitting our sample below 0.002%. That is a microscopic 20 parts per million. Insane precision, right? All right, Section 4, the pyrolysis procedure, thermal decomposition. The baseline for this whole reaction is just intense heat. We've got to heat the furnace up to a constant, rock-steady temperature of 600 degrees Celsius. That is over 1,100 degrees Fahrenheit. This is the extreme environment where the plastic polymer chains literally shatter and vaporize, leaving only our target material behind. Timing and pacing are everything in this lab. First, we quickly open the tube, slide our boat in, and shut it fast. Then we have to rush a heavy flow of nitrogen through for 5 solid minutes just to purge any room air we accidentally let in. Then the tube slides right into that 600-degree furnace zone. For at least 15 minutes, the sample bakes. The plastic vaporizes, but then we have to slam the brakes. We pull the tube out of the heat, and while the nitrogen is still flowing, we wait for 5 agonizing minutes as it cools. Finally, we move the boat to a desiccator, a totally dry, sealed chamber for 30 full minutes. Why so agonizingly slow? Because if that boat is even slightly warm, or if it absorbs even a microscopic drop of humidity from the room air, our final weight is totally ruined.
And that brings us to Section 5, Calculating Content, Carbon Black Percentage.
Ultimately, this all comes down to the 4 W's. These 4 critical mass variables. Let's break them down real quick. W1 is just our empty combustion boat. W2 is the boat plus our initial chunk of raw plastic, usually about a gram. W3 is the mass of the boat plus the black residue left over after that intense nitrogen burn we just went through. And finally, W4 is the mass of the boat and residue after burning it again, but this time in normal everyday air. So here's how they all tie together in our gravimetric formula. By subtracting the empty boat weight, W1, from all our other variables, we isolate just the masses of our sample and our residues. Now here is a truly fascinating little caveat to the standard. For most samples, the math is super simple. But if a manufacturer suspects their plastic has less than 1% carbon black, they actually have to take that leftover residue from the nitrogen burn and put it into a muffle furnace to burn in normal air. That creates our W4 variable. Burning it in air completely oxidizes and destroys the carbon black, leaving only inorganic impurities behind. By subtracting that inorganic ash, W4, from our nitrogen residue, W3, the standard brilliantly corrects itself, making sure we're only calculating pure carbon black.
So what's the payoff for all this intense setup, careful purging, and meticulous weighing? Unbelievable accuracy. The standard states that the interlaboratory precision of this test, meaning a lab in New York and a totally different lab in Tokyo could run this, is plus or minus 0.156% for materials in the 2.5 to 3.0% carbon black range. That exact tiny number proves the incredible value of having such strict standardization. When you follow the rules of ASTM D1603 to the letter, the science absolutely does not lie.
So the next time you're out and about and you spot a heavy-duty black olefin plastic, maybe a water pipe or a tough industrial container, take a quick second to appreciate the hidden scientific rigor behind it. Ask yourself, just how much carbon black is actually locked inside that structure, and has it been proven by the fires of ASTM D1603? Thanks so much for joining me on this deep dive today. Keep learning, and I'll catch you in the next explainer.